klockan på exakt 9.00 så att då kör vi igång dagen. Välkomna tillbaka alla. Jag hoppas att ni hade en fin kväll igår. And I would like to welcome again our international guests, new and old ones. You're very welcome. The conference language is Swedish, so I will continue soon in Swedish, but I just want to say who I am. My name is Cecilia Lindhé, and I'm director and researcher at the Center for Digital Humanities here in Gothenburg, and I will be moderating today's sessions. För er som är nya idag, lite säkerhetsinformation bara. Nödutgångarna här, bakom er, den i mitten, huvudingången. 2 här nere, 2 där uppe och 4 bakom mig, 2 där uppe och 2 där nere. Återigen, har ni några frågor eller så kontakta arrangörerna eller mig. Går det bra att fråga också. I eftermiddag kommer jag att försöka sammanfatta de här 2 dagarna. Och det är en utmaning. Men redan nu vill jag ändå lyfta den spännvidd som gårdagens talare bjöd på. Lars Ilshammar inledde med 3 punkter för hur vi ska skapa världens digitalaste kulturarv. Han menade fina ord som demokrati och så räcker inte. Vi måste vara mer handfasta och konkreta. Han menade också att vi måste enas om en långsiktig nationell digitaliseringsplan, men betonade också vikten av att anpassa format till olika användares behov. Flera presentationer handlade om VR och AR. Vi fick se spännande, nydanande exempel, både nationella och internationella. Viktor Lindberg historiserade den här nya tekniken när han visade på parallellen mellan dagens immersiva teknologier och fantasmagorier och andra bländverk under 1700-talet och tidigare. Vi fick höra om nya experimentella plattformar, filmarkiv, staden Platsen, den samtida och den historiska, stod i fokus såväl för ett arkivperspektiv som gestaltningar i 2D och 3D. En gemensam nämnare för flera presentationer tyckte jag var en syn där det digitala och analoga, om vi nu kan använda de 2 begreppen, allt tätare vävs samman och problematiseras. Och det här är något som jag vill återkomma till i eftermiddag. Men nog om det nu. Det är ett späckat och synnerligen intressant program idag också. Och jag vill börja med att introducera vår första talare. So I would like to introduce the first speaker of today. It's Barmak Heshmat. He was a former researcher, scientist at the MIT lab. He's now CEO of his own company, BRELYON. And he's going to talk today about emerging technologies and applications for batch scanning of documents. Welcome, Barmak.
Thank you so much. God morgon. Great. I'm Barmak Heshmat. I was a research scientist at MIT Media Lab, and some of the technologies that I'm going to introduce you today is from MIT. Currently, I am the CEO of my company called BRELYON, which is bringing a new category of displays to the market that is going to disrupt AR, VR, and 3D displays. Before I can explain to you the technology that I'm going to introduce, I have to talk a little bit about imaging and time, and imaging and frequency. So if you think about imaging is such a fundamental concept. I mean, we invented the microscopes and the telescopes that revolutionized our understanding of biology and outer space. So imaging is all about spatial domain, where you're basically looking into microscale or macro scale. But what about time? The time dimension have not been explored as much until recently. As the electronics got faster and faster, the cameras were able to capture images much faster. So we're starting to see more applications and capabilities that are enabled by time. So when I talk about fast cameras, how fast do I mean? Well, the fast is a relative term. So a fast camera depends on who you ask. If you ask an electronics engineer, he or she would say 1,000,000 frames per second is as fast as an electronic camera can go. If you ask a physicist, he would say, bah, that's nothing. A zeptosecond is as fast as you can have an X-ray pulse, a very short X-ray pulse. But if you ask me, an optical engineer, we would say about 1 trillion frames per second. That's where ultrafast is for us. So this video is captured at about 500 billion frames per second. And you can see a pulse of light passing through the Coke bottle. At these speeds, you can actually slow down the light and see the light itself as it's traveling. So this obviously has a lot of applications in imaging through scattering medium, imaging through complex geometries. But the first perk, the first advantage that you have when you have very high-speed imaging is depth. Because an object that is further away from your camera takes longer to be seen by your camera. So you can send a pulse of light and wait for it. And then if the object is sending a light later in time, it means it's further away. If it's sending the reflection back earlier, it means it's closer by. This is actually the principle of LiDAR, which is one of the methods to do 3D scanning for autonomous cars. So these systems also send a laser, and they scan the environment with laser, and they extract the phase from the reflection of the laser that is coming back to the sensor. So my research was on exploring this time dimension. What else can you do with this time? What does it mean to have a camera that has 500 billion frames per second? What is an optics? What does the lens of a camera that has such a high speed look like? So these were at the core of my research. Can you use this time resolution to scan through the body? Can you use this resolution to image through complex geometry, like, for example, under the rocks or in the rubble? So I did a lot of research and published a lot of papers, and you can find these papers if you just search my name and add MIT to it. And if you needed any of these publications, I can just send them to you if you don't have subscription to the journals. So now that we talked about time and the time scales that I'm talking about, let's talk a little bit about frequency. So everybody knows about radio waves and electromagnetic waves, right? So these are waves, electromagnetic waves that have different frequencies, and we have the spectrum of these electromagnetic waves. So for example, your cell phone works with microwave, your remote controller at home works with infrared, TV emits light invisible, which is what your eyes can see, and higher than that is ultraviolet, which tans your skin in the beach. But what I was mostly working with was this very new kind of gap in the electromagnetic spectrum that is being explored in the recent decades. And that's called terahertz wave. So terahertz wave is from 100 gigahertz to 10 terahertz. So these frequencies were much more difficult to generate until a couple of decades ago. So there were no light sources, no lasers and sensors to detect these radiations. But in the last 2 decades, there have been a lot of breakthroughs that is making this frequency range more available. This frequency range is being used right now for 5G, actually, the next generation mobile communication data transfer that is coming to your cell phones in a couple of years is going to use these frequencies, which is around 80 gigahertz. So it's on the lower end of this frequency range. And from this whole spectrum, you can do imaging and inspection. You can use it to study dynamics of semiconductors and so on. So when you take an image of an object with these frequencies, you start to see new colors, new absorption spectrum. And one of the applications of this is actually doing water profilometry. So you can see on the image on the top left is the image of a leaf. And when you look at it in terahertz, you can see that the portion that is dry is showing a lot of contrast because water is absorbed with terahertz very, very strongly. Or for example, on the top right, you can see that there's a mixture of toothpaste and moisturizer. To the naked eye, they both look white, so you cannot tell them apart. But when you look at terahertz spectrum, you can see that one of them is absorbing significantly. The moisturizer is absorbing the terahertz while the toothpaste is not, because it doesn't have as much water in there. You can also look inside the plastic or wood or paper with this frequency range. So for example, you can see that I can see inside the IC, the chip on the circuit board. Obviously, one of the first applications is to do inspection for security. So for example, if you actually shine these radiations to people, you can see through their clothing. So it's an interesting capability. But you can also use this to do inspection, for example, in the airport. Now there are several systems that is coming out that use millimeter waves or lower end of the terahertz spectrum to do scanning. Why is this better than X-ray? Because X-ray is ionizing radiation. Every time you get an X-ray scan, you're increasing your chance of getting cancer. But terahertz or millimeter wave, they have much lower frequency. So the power is much, much lower. So it's not ionizing your DNA. Another application, which I guess would be very interesting to you guys for these frequency range, is inspecting cultural heritage and artworks. So this is one of the research that was done in Spain, I believe, with one of my colleagues, Albert Rito Sanchez. And he basically, what he did was he scanned this painting from Goya, and he could actually extract a signature beneath this painting. So you cannot see this with the eye, but when you do this scanning with terahertz, you can actually see deeper layers of the painting, very much subsurface. And you can extract, for example, you can see that there's the signature there that can authenticate this artwork. So it can be used for authentication of the artwork. But it can be used for other things. For example, you can extract the information about the subsurface to see what is the structure of the paints, if there are any gold painting beneath the dirt. So this work, which was done by Danish Technical University, they used terahertz and they compared the results with infrared reflection and showed that terahertz can show you deeper within the surface, but also can show contrast between different material much better than other radiations. So you can see, for example, if there is gold and you want to clean this, or if the painting is very thin, you know how you should clean this. You have information about the structure, about the edges of the colors, and so on. Obviously, X-ray can also do some of these applications. So for example, this is another artwork from Picasso, The Blue Room, which was scanned with X-ray. And once scanned, you can see that there was actually a previous painting that Picasso have done below this painting. So this kind of scanning can actually tell you a little bit more about what is the history, what was going in the mind of the artist when he was creating this artwork. And did he correct anything? What is the story of this artwork? And you can see beneath that woman was a bearded man that Picasso has probably changed his mind and draw over it. So what I want to talk more specifically today is batch scanning, which is not just for seeing one layer below the painting, but how can you actually scan many, many layers, like scanning through a closed book? Can you actually see through a closed book without mechanically opening it? So we want to go from something that looks like that, like on the left, stack of pages, to the right and read the letters automatically. There are many methods to look through layered structures, okay? X-ray is one, for example, X-ray tomography. This is an example system that can do that, for example. It's from NSI X-ray systems. And usually the problem with X-ray is that, first of all, you have a very gigantic machine. It's very expensive. It is hazardous. So you cannot just wander around and work with it freely. It has to be in a concealed environment. And another issue that it has is that X-ray doesn't give you contrast for a lot of inks. So if you have a text, a document that is written with, I don't know, like blue pen or certain types of inks, which is not metallic, then you're not going to be able to pick up that information with X-ray. So that's why X-ray would fail. Infrared, on the other hand, is another method that you can use to scan through a batch of documents. But the problem with infrared is that it can't penetrate very deep. It gets absorbed with the paper. So it cannot go more than like 2 pages. But the advantage of infrared is that it's cheap, it's small, it's not hazardous, and it has a very high accuracy. Ultrasound, it penetrates very deep, so you can see the defects within a very large stack of pages, but you cannot read it. There's no electromagnetic signature, the resolution is very low, and that's why you cannot extract the information. So that's why we went to terahertz, this new emerging piece of electromagnetic spectrum. And this is the system that we have. So we have a stack of pages, and we're sending a pulse of light, which is in low frequencies, into this stack of pages. This stack of pages is completely compressed together, so there's no artificial gap that we have added. It's like just like a closed book. And once we're sending this pulse into this stack, we're getting reflection from each page. So the deeper page will give you reflection at a later time. Just as I explained to you at the beginning of this talk, if the page is further away or is deeper inside the book, it would take longer for the light to come back. And because we have a very, very fast camera, we can actually see that. So we can differentiate between different pages in time. Once we have that, we can actually look at the frequency components of the pulse. So we take Fourier transform and look at the frequency components of the pulse, and that would tell us if there is ink at that point or if it's blank. So what we're doing here is that we have this stack of papers or book on an XY stage. So this pulse is being is shining on one of the points, and we are scanning, raster scanning. To explain a little bit how this terahertz system works, this terahertz system is an electro-optical system. It's not a normal LED or laser diode. The way it generates these frequencies is that it's triggered by an infrared pulse, and these infrared pulses excite a fast semiconductor, and that fast semiconductor emits these lower frequency radiations that we can use. And we get a pulse that looks like this, basically. When I was at my PhD, these systems used to be gigantic, so they used to look something like that. But as the years went by, we're getting more and more smaller and smaller versions of these devices. So you can see this is a desktop model that you can get from one of the companies. There's even handheld model now. And some research is being done to do like very, very small chips that can give you terahertz. And as I mentioned, Qualcomm, which is one of the biggest chip manufacturers in the world, is bringing terahertz or lower frequency of the terahertz to your cell phones in a couple of years, so you can get more bandwidth. So in order to read through closed books, you have 4 major challenges. First of all, you're dealing with a very low signal-to-noise ratio, so you don't have much light. You have to be very careful. Second is you have a phase distortion, because the pages are not perfectly flat. If you look at the book, on a microscopic level, the pages can be warped a little bit. So that means that in that time resolution that you have, you're going to have some waviness that you have to deal with. The third issue is ink contrast. Can your frequencies actually detect that ink? Because if it cannot detect that ink, then you cannot say what is the text on that paper. And fourth issue is the shadowing effect. If the letters on the top surfaces or top pages are absorbing the radiation, then you cannot see what is below them because the radiation is already absorbed. So you're dealing with shadows and occlusion. The image that you're getting, it looks something like this down there, and you can see there are many issues. So for example, that letter L has part of it missing, right? So you have this part missing, and you have a shadow of front pages, which is not for that page, and you have some distortion and noise. And that's the cross-section that we're getting. So that horizontal axis is time, and the vertical axis is x. So you can see the pages that they're giving you signatures in time. We developed a statistical model, which I'm not going to talk in detail, which basically extract these pages. So you can lock into individual pages and get rid of the shadows from the other pages. So you're sure that the signal that you're getting is from that page. And then what we did was we used a computational method to look into the frequency domain and see which are the frequencies are absorbing the light with strongest signature. So we average those frames to enhance the contrast. So you can see that we can go from something that looks like on the right is very noisy, right? We can go to something that has much better contrast on the left. So we put 9 pages of information on top of each other, and this technique could automatically read these 9 pages. And in this paper, we basically showed that how different inks and different papers can have different contrast level and how many pages you can read at what level of signal for these papers. So this is the data. You can see that there are different methods and they're extracting the letters automatically, right? So this is page 2, page 3. So again, there are 3 steps. Log into the page, enhance the contrast, and read the letters. Page 4, page 5, and this goes all the way down to page 9. So you're reading a book page by page without mechanically opening it. So this video summarizes.
In order to read through a closed book, you have to do 4 things. First, you have to have a radiation that goes through the paper. So the paper has to be slightly transparent in this frequency range. Second, you have to have the time resolution to distinguish between different pages. With this time resolution, we can actually separate the pages. We can look at very, very small objects. The pulse that you send in is going to be reflected from each of these air gaps after each page. And we try to separate the pulses that are actually from this air-paper boundary compared to the noise that is coming from the rest of the sample. Third, you have to have the spectral information of different inks. For example, the ink should be visible in that range of frequencies. And the fourth one is recognizing the characters themselves. There is a shadow of different letters on top of the next page. So the algorithm has to be able to recognize the characters, although some part of the letters is missing.
So this has applications for inspecting antique books or antique documents, which you cannot mechanically handle. You cannot mechanically touch it. It also has application for counting money, counting the bills in the bank. So you don't have to have a mechanical robot that counts the bills. You can just send a pulse and it will count it at once with a press of a button. So this is a technique that we have invented. It's called batch scanning. And you can read about this if you want, read about this more on Nature Communication. I believe it's an open access publication. You can download the algorithms and everything is there. So here are some of the companies, if you're further interested about these radiations and using this for inspecting artworks, these are the companies that you should be looking for. So these are the companies that generate sources or terahertz systems that can do this type of scanning. So Hamamatsu from Japan, Zomega from New York, USA, and a lot of companies in Europe, Baytab, Mello System, Toptica, these are all from Germany, and TerraView is at Cambridge, UK. So they're mostly actually very close to you guys. All right, so I talked about some of these more advanced imaging techniques. Now I'm going to talk a little bit about more commercialized end of batch scanning. Scanning documents in large volumes is a very interesting and lucrative, actually, business. So there is a company, a startup, that is providing a service to do batch scanning. So this company called Ripcord basically takes your archives, if you have any archive of documents, and it has certain robots that they scan these pages and upload the information digitally to the cloud in a way that is searchable to your organization. So I'm going to play this video that kind of introduces this startup.
I think the future for Ripcord is capture it all. You know, we want to be the company that takes the entire world paperless. And I think we have the technology today and the technology approach of the future that can make that possible.
Our number one differentiator is that we use robotics to digitize paper. No one else in the industry is doing that.
A lot of companies build fast scanners to scan pieces of paper that are in a nice stack, all of pretty much the same type. Nobody else is using robots to do this.
You take a stack of paper, you load it into these machines with all of the fasteners attached, and the machine looks for the fasteners on every single sheet, removes them with an end-of-arm tool, and then moves those single sheets, once the fasteners have been removed, into our scanning systems, which scan at 1,000 dpi. It's the highest resolution scan in the industry.
What we are trying to do is show the world that there's another way that you can access this data, that you can have this data forever that's not on a sheet of paper. And it's more secure, and it will last longer, and it's safer, and it's at your fingertips.
We're able to take all that information, ingest it into our cloud platform, and make the data available to the customer.
I realized that we had the potential to build not hundreds, but actually thousands of these machines and be able to do something really powerful, which is connect that data into businesses and governments and people who need access to that content, and humanity would benefit.
Everything that we're doing is about preserving the content, making it accessible, and connecting it to real value.
So this is Ripcord. And what's interesting about their technology is that you can give them the archived material with all the staples and all the clips and everything, and they will preserve that data digitally. So they can tell you which pages were stapled together, and the taxonomy of that document is preserved. And that's what's different from a conventional scanner. All right, so I realized that there was a lot of talks on AR and VR, and I'm an optics engineer, so I work a lot with light, and I have a company that actually works with new categories of display. So I wanted to talk a little bit about AR, VR, and what I am doing. So the company name is BRELYON, and we're really reimagining displays, and we want to go beyond the problems that AR and VR has. Some of the problems that I saw less people talk about is the issues that AR and VR headsets have for public use cases. So one issue is that VR headsets, they are fundamentally isolating. When you put them on, you cannot see anything. So if you're walking around, you may actually hit the table or hit the wall, and you're not aware of your surrounding. They're very bulky. They're not sanitary. If you have a VR headset and 200 people are putting this on their faces and they're sweating, and it's just a dirty thing that you don't want to put on your face. And they're also uncomfortable. Right? So nobody wants to wear a gigantic brick on their face for like 8 hours a day, right? So that's one of the issues, some of the issues with VR headsets. AR headsets, on the other hand, they let you see your environment, so they're good in that sense. But usually, they're still limited in their technology. They have very small field of view, which means that you only see a very small portion of the virtual world as you're looking around. They're computationally very expensive. It means that they need a very powerful computer to match the virtual content with the real world. And they usually give you poor image quality. The image is hazy, it's a little bit has this halo, it's kind of not very pristine image quality. So what my company is doing is that it's exploring the question that, is it possible to give immersion without headsets? can you experience something like virtual reality or augmented reality without having to wear any headsets? Because if you can, then that would open a gateway to, really new experiences that are more functional, that are not just gimmicky for games, but there's something that you can actually use on a daily basis for 8 hours. So in sci-fi, the visualization, the 3D visualization is abundant. You can see it from any angle, you can interact with it, and that's where you would hope to go. But what we have today in reality is these autostereoscopic 3D displays, which are giving you artifacts. You have to sit at a very right angle to see them correctly, and sometimes they need glasses, which completely contradicts the purpose of having a screen, because you can now just wear VR headset instead. So we want to really see why 3D failed and solve these problems so we can get closer to that abundant visualization. So I'm glad to say that BRELYON is providing the solutions and the technologies to provide that abundant visualization, which is going to fundamentally transform how you explore artifacts in museums, how you work with your daily minders, how you perceive digital information. And that's kind of our mission. I cannot tell you about what is our product because we're still in the stealth mode. But if you're interested, you should definitely come and talk to me. So thank you so much. And if you want to engage, you can either download the slides or book a demo or pre-order some of these products or start a collaboration. You can just email me. Thank you so much.
Thank you so much. We do have time for questions, so please, go ahead.
Okay, should be on, I guess.
Okay.
Yes.
There it is. Stig Storell from Norwegian Directorate for Water Resources and Energy. Is this in any way applicable to photographic material? Because photographic material, as you know, is layer-based, the photographic negatives and photographic positives. Have you or anyone else researched the application of this technology, the terahertz, on photographic material?
This is a very interesting question, and I believe that there should be notable differences between different photographic materials, but it also comes down to what is the thickness of the layer that you're talking about. If you're only interested in, for example, seeing how the photographic material has been decomposed, then terahertz can be actually very interesting. But if you're interested to, for example, separate the layers that are less than around 50 micron, then you're going to have trouble. So in short, there's definitely a lot of potential for exploring that direction. I don't know of anyone that has explored photographic materials, but any material that has polymers inside it is usually interesting for terahertz range.
I was wondering in connection to that, when it comes to the terahertz scanning, what would be the biggest size of the object and from how far? Because I'm thinking whether you want to see if there are an old Viking village somewhere outside of Gothenburg and you want to scan a big area. Would that be possible with this technology?
That's a very good question, and it's actually a very technical question. So the distance that you can operate these scanners depends on what is the frequency range of these scanners. If you're going to higher frequency ranges, usually you would prefer to be at a shorter distance. But if you're dealing with frequencies that are lower, for example, 1 terahertz and lower, from 100 gigahertz to 1 terahertz, you can actually have a very large distance from the camera or from the spectrometer to the object. And in terms of the size of the object, because the scanning is a raster scanning, the system is agnostic to the size. It depends on what is your automation stage, or you can do like patch by patch and scan a very large object.
Interesting.
Yeah? Any other questions?
Would it be possible to combine this technology with AI, for example, computer vision, to see
Absolutely.
patterns and different kinds of motives in artworks or?
Absolutely. So there is a lot of research going on using machine learning for character recognition and or any pattern recognition, right? So any research that has been used in visible domain or in infrared domain for character recognition can also be applied to terahertz. There's not much difference in that sense. The only difference is that you have time information as well as the spectral information. So you not only have the contrast for the ink, but you also have the structural information which you can use. So you're dealing with a data cube, not just the image.
It's really, really interesting and mind-blowing in so many ways. Any more questions?
Oh, yes. There's one there.
Thank you.
Yes, I'm wondering about, how is it the penetration when it comes to certain materials? I'm thinking if you're scanning medieval parchments instead of books, and you have illuminations in gold foil and such things, can it penetrate, or does it just reflect? So is it possible to scan through a pile of those kind of parchments where you have those kind of like gold foils?
Right, yes. So the question that you're asking is, how deep can I go?
Yeah.
And this is, again, a matter of what material is being scanned, right? So if the material doesn't have a lot of absorption, let's say it's wood-based, so it's a paper or it's a wood, then with a typical spectrometer, for example, the ones that I show from some of those companies, you can usually go around 1 centimeter. So that's with very good computational methods, you can extract structural information down to 1 centimeter. But if you want to read it, if you want to actually scan the pages and read it, then you're talking about 5 millimeters or something like that of information that you can read. But it also depends on what is the ink. For example, if the ink is made of carbon-based materials, or if it's metallic, then you get much more contrast. But if the ink is made of some sort of polymer or something like a modern pen ink, then your contrast is lower. But usually that's not the case for old documents. Usually the old documents are based on carbon-based or metallic or something like that. Yeah. But again, this is also a matter of signal-to-noise ratio. So if you, for example, want to read 2 centimeter or 3 centimeter, it is definitely possible. By the way, 1 centimeter is from one side. So if you, for example, flip the book, you can do another centimeter from the other side. But again, it depends on how much power you have. If you have a customized system, if you have your own laser and if you have your own spectrometer, you can increase the power to read deeper. Yeah.
I'm sure you will be able to answer more questions during the break.
Absolutely.
You will be able.
We'll be happy to talk.
Yes, thank you so much.
After this.
Great presentation.
Thank you so much.
Thank you. Thank you.